Good morning, all of you TyBsc physics student. Today we want to continue our third chapter, which is free electron and band theory of metals, and we want to continue the point which is distinction between the metals, insulator and the semiconductor. Now summary of the last lecture, we have given this expression which is considered as the n effective, which is considered as 2 into L upon 2 pi minus k1 to plus k1 fk into dk, and that fk value which is nothing but the m upon h cross square d square e divided by dk square. So we want to put this value in, for example, this is considered as the equation number 2, and this value which is putting in the equation number 2, so that is considered as, if we see here that 2 present is there and 2 also is there, that 2 get cancelled. So that given this formula, that n effective is equal to given this L upon pi is here. Integration limit we have to consider that here integration limit is minus k1 to plus k1, and that integration which is considered as the limit minus k1 to plus k1, and this limit which is considered as the even limit of the integration, that fk value which is considered as the m upon h cross square d square e divided by dk square, into that integration with respect to that dk. If we have to see here that even limit of this, so that we have to this limit convert into 0 to k1, and if convert into 0 to k1, that 2 which is get the outside of this integration, so that n effective is equal to 2 into L upon pi, that integration which is given as 0 to k m upon h cross square into d square e divided by dk square into dk. So we have to see solving for this integration, so that next term we have to obtain here, so that n effective is equal to twice L. So this m upon h cross square, this is also constant factor, so that factor which has given the outside of this integration, so that n effective is given here twice ml upon pi h cross square, integration of 0 to k1. So that here we have to see that term d square e by dk square, so we have to getting outside that d by dk into de divided by dk into dk. Okay, so that d by dk, this dk that get cancel this term, so that, or this integration which will have here, so that integration limit, that de divided by dk, so that value of the integration or the limit of integration which is considered as that k is equal to k1. So this is the integration given for the effective number of electrons by doing calculation for this twice ml divided by pi h cross square de divided by dk. And this equation, so for example, this is given the new equation number, that is equation number 3rd, and this equation which is conclude that the effective number of electrons in the completely filled band is 0. What is the effective number of electron which is completely filled band is 0? So that is see with the help of the clear understanding, with the help of the diagram or graphical representation. So that first conclusion, the effective number of free electron, the that conclusion number first, the effective number of electrons, the effective number of electron in completely filled band, in completely filled band is 0, is 0. So that diagram which is considered as the completely filled band with the number of energy levels, so that is a graph which is represented as that vertical axis which is considered as the energy eigenvalue, and which is vertical axis which is horizontal axis which is considered as the k value. So that according to definition, so this completely filled band, so that we have to consider that the limit value of this k is equal to minus pi by a and k is equal to plus pi by a. So this is the limit of the Bilwa zone, or considered as the Brillouin zone, and energy at the value for k is equal to 0, that energy which gets 0, so that this point energy 0 and k is equal to minus pi by a and plus pi by a, so this value should be get maximum. So this is the graphical representation which is as act like this. And according to definition for first derivative, that which is depends on this, that dE by dk is 0, and this condition which is obtained from the condition of the maxima or minima or the point of inflection. This is very interesting point which is come in the MMP or mathematics method in the mathematical physics, that we have to get clear this point. So for this, the completely filled band, and according to this definition, that first derivative is equal to 0, so that's why this completely filled band is 0, and that which is given by that dE by dk. For this condition, dE divided by dk is equal to 0, dE by dk is equal to 0, and that condition the n effective is equal to 0. So that is the expression and that diagram which is considered as the completely filled band figure, which is completely filled band. So we have to consider here now second conclusion, which is considered as the effective number of electrons attains a maximum value when this band is filled up to the point of the inflection, So that second conclusion we have to see here. So that conclusion number second, the effective number of electrons conclusion number second, the effective number of electrons attains a maximum value value when band is filled up to the point, when the band is filled up to the point up to the point of the inflection. Point of inflection. So first point which is considered as the effective number of free electrons which is completely filled band is 0 when this d by dk is 0. And next conclusion, so this effective number of the electrons which is maximum, that value when the band is filled up to the point of inflection, that point of inflection which is nothing but we have to see that idea. So for the concept of the maxima and minima, that for example this is curve which represent as the minima here, that this is point which is considered as the stable equilibrium point. Again point which is considered as this point which is considered as the maximum point. So that for this point which is the minima, this point which is considered as the minima, and this point which is considered as the maxima, this point which is considered as the maxima. If we see this point which is considered as the stable equilibrium, this point which is considered as the stable equilibrium, and this point which is considered as unstable equilibrium point, unstable equilibrium point, and that which is obtained from the expression of that gives the slope, that slope which is considering as that the first derivative of this point which is dE by dk is 0, and this is also equal to dE divided by dk, or whatever expression that is equal to 0. And second derivative point, that d square E divided by dk square, which is get here the positive for the minima, and d square E divided by dk square is negative for this. And the we want to see here the our point which is considered as the what is mean by the point of inflection. So that point of inflection which is nothing but so that point which is considered as the, for example, position here, so this is considered as the point of inflection, or for example in this curve, this point which is considered as the point of inflection. So that point that is considered as this point which is not maxima or not minima, or this point which is considered as the point of the inflection. And for this point, that conclusion we have to see here the effective number of electrons attains a maximum value. So we want to see here the graphical representation of this, the completely filled band, and this band which is not completely filled, that is the half filled band, that is the maximum value, and that given value which is given as here. So that vertical axis which is considered as the plus E, and that band value your limit which is considered as the k is equal to minus k1 and k is equal to plus k1 as the first graph we have to see here. And this is considered as the minus Ka plus Ka for the lattice constant value. And if we have to see in this figure, that energy which is filled up to the half, so that is given by the understanding concept by the second conclusion, which is considered as this value which is maximum at the point of the inflection. So why consider the point of inflection? Because this point, as both of this point, that band is filled, and this band is filled up to the point of inflection, and this point which is considered as the point of inflection for both curve. So that is the analysis of this figure, and that figure which is considered as the band filled up to the point of inflection. The band filled up to the point of inflection. Okay, now next point we want to see here, so that is the diagram of the insulator, semiconductor and metals, or with the help of this diagram, with the help of this band diagram, so we have to analyze. So that is what is meant by insulator, semiconductor and metals. So that from above this discussion we can say that certain number of energy band which is completely filled and all others are absolutely vacant, which is considered as the insulator, and the band which is formed by series of energy levels containing valence electron, this band which is considered as the valence band, and the on the top of this valence band which is considered as the conduction band, and the energy gap between the valence band and conduction band which is considered as the forbidden gap, or which is considered as the energy gap, or which is considered as the band gap. So the energy gap between, so for example we have to see here the rough figure of consider as the valence band and conduction band. So this is considered as the energy which is considered in the electron volt, and this band which is considered as the valence band, because outermost orbit electrons which is present in this band, so this is considered as the valence band, and above of or top of this band which is considered as the conduction band. This is considered as the conduction band. Okay, and if we see that the region between these two band which is considered as the band gap, which is considered as this region which is considered as the band gap. Okay, or which is considered as the energy band gap. So that here consider the energy gap between the valence band, that point which is considered as the energy gap between valence band and conduction band, is called band gap. So if we distinction between this figure which have that figure which is considered as the 0 degree Kelvin, so that the presentation of the energy bands at consider as the metal, semiconductor and insulator, which is we want to see here. So that figure which is considered as the representation of the energy band. Representation of energy band, and that figure which is considered as, for example, this is figure first we want to consider for the insulator. So for insulator, the first band of the bottom of this which is considered as the valence band, and the distance between or band gap between the conduction band and valence band, which is more as compared to the semiconductor or metals. So this is considered as the band gap or band diagram or the representation of the energy band of the insulator. So that is considered as the insulators, and this band which is considered as the valence band, and this band which is considered as the conduction band. And the value of the energy gap which is considered as the band gap energy between these two band, which is considered as Eg is equal to 6 electron volt. So that band gap value between these two band, so that is considered as the energy gap, and this is considered as the 6 electron volt. Now next band which is considered as, or next diagram which is considered as for the semiconductors, for semiconductor material, and that semiconductor material, so that how this bottom of this band which is considered as the valence band, that outermost shell filled electrons which is present in this. If we see in insulator, that electron which is not have energy or not much have energy, which is go from valence band to the conduction band. And if we the semiconductor, so that is this representation which is ideal at the 0 degree Kelvin. But if we see in the semiconductor, if we that certain increased temperature that we consider as see as the at the room temperature, so that electrons have some achieve energy, and that possibility of this electron which is jump from this valence band to the conduction band. So this is the property of this that some of the material like the semiconductor. So now this as compared to this insulators, so that the energy band gap between these two band, which is as compared to this which is small, so the top of this valence band, so next band which is considered as the conduction band. Okay, so this is considered as the valence band, and this is considered as the conduction band, and this is the energy axis which is considered in the electron volt. And the energy gap, that is the band gap energy between the semiconductor, which is considered as nearly equal to the 1 electron volt, which is nearly equal to the 1 electron volt. And for this insulator, so that example of insulator which is considered as the, for example, diamond, aluminum oxide, that is Al2O3, that etc., the example of this insulator. And this is the semiconductors, and that example of semiconductor which is considered as the silicon germanium. So here example which is considered as the diamond. So for example, if we see here that the band gap in value for this silicon which is considered as the 0.3 electron volt, and for germanium which is considered as the 0.7 electron volt or whatever there, so that the distinction between this insulator and semiconductor. Now next figure we have to see here, that the representation of energy bands in the metal, and that representation in the energy band of metal as compare to these two figure, so that the band gap which is not that consider not band gap which is presented in which is metals, because of this conduction band and valence band which is overlapping to each other, so that is the next condition which is considered for the representation of the bands, energy bands which is considered in the metals, and this lower band which is considered as the valence band, and upper band which is considered as the conduction band. I want to draw, this is different types of the suasion, so this is considered as the conduction band, and that value of energy which is considered in the electron volt. So that is the overlapping of the conduction band and valence band, that property which is show that the metals, and that example which is considered as the aluminum, copper, that etc. So that important notes have, see here, the conductivity of semiconductor which is increase with increase in the temperature. So that is already we have to see here, or I have to explain you that if we that increase temperature for certain 0 degree Kelvin to up to the room temperature and above this, so that electrons which has possibility that jump from valence band to the conduction band, and that is known as the increase the conductivity of that material. And this is because the increase in the temperature, and more electrons which is jump from valence band to the conduction band. And conductivity of metal however decrease in increase the temperature, and this is because the increase in temperature, more and more phonons which is excited which scatter conduction electrons, and so reduce the mobility of the electrons. So up to this we have to clear that idea. So what is the band theory of metals, and up to the this lecture, so your chapter is also complete and your syllabus is also 100% complete. So best of luck for the next exam. So thanking of you.